Okay, so starting today, going over page 605, number 20, and we're still dealing with complex and polar roots. And the question is, how do you use de Moivre's theorem to deal with something like that? I changed the directions in the book. The book said put your answer in rectangular form and only find the principal root. I said leave all answers in polar form and find all the roots. So the first thing you need to know is what is this in polar form? What's -1? Let's do a visual. You've got an y-axis, you've got an x-axis. Here is -1. How far from the origin is that?
1.
What angle is that?
Pi over 2.
Pi over 2 is up here.
Pi.
That's just pi. So this is which is 180, which I also heard. So 1 cis pi is the point we're talking about in polar form.
Would it just be cis pi? Could you write it like that, or would you have to put the 1?
You don't have to put, that's a good question. I don't think I've ever seen just cis pi, but you shouldn't have to put the 1. I'm not sure. Let's put it to be safe. Now, the rule is, with de Moivre's theorem, is first you find the principal root by taking the 4th root of your distance from the origin, and then 1/4 times your angle. So we start out saying the 4th root of -1 is 1 cis pi over 4. Remember that first lesson I told you on where the imaginary plane comes from? On how if you take the square root of -1, you have to wind up here at 1,90 in polar form, right? Take 180. Does it sort of make sense then that the square root of this, okay, if the square root of -1, if the square root of this idea of being 1 out in the direction of 180 degrees is 1 up 90 degrees, does it sort of make sense that the square root again would go to 145? Because that's what this point is. 1 unit from the origin at an angle of 45 degrees in the complex plane. Took the square root of -1, got here. Took the square root of I, got here. That's what a 4th root is. It's a square root twice. What do you think would happen if I took a square root again? Where would I be? Well, I'd be halfway to the x-axis again. So that would be 1, 22.5 degrees. So if I kept square rooting, I would keep cutting the angle in half and keep going around this circle. Keep getting closer and closer and closer to 0, but not quite getting there.
Wait, so think that cubop thing Bob you talked about?
Yes, this is Zeno's paradox, but we won't go back to that yet. That comes later. But at any rate, this part is not part of what the problem asked. What the problem asked for is just for the principal root of -1 to the 1/4 power, which would take me to 145, or 1 cis pi over 4. How many roots does this thing have?
Oh, wow, look at it.
How many roots, Nathaniel? 4 he's holding up. Okay. What did I say about finding the other 3 roots? They are
90 degrees.
It'll be 90 degrees. Why? That's correct. 360 divided by 4. The key thing I should remember is they are evenly spaced about the origin on a circle. So if one of them's at 145, you guys are right. I'll go 90 degrees from there to 1 cis 135, 3 pi over 4. Then there must be one down here at 1 cis 5 pi over 4. And finally one over here at 1 cis 7 pi over 4. So if I change the directions, the directions just asked for this in rectangular form. I said don't do that. Leave it in polar form. And give me all of them. Any questions on that? You get 4 evenly spaced answers all the way around. In this case, a unit circle, a circle of radius 1. So those are your answers. Any questions on that?
No.
Where I got any of that? Was there another one?
24.
24. It's almost the same question. Almost. Let me know when I can erase this.
Yeah.
I'll have a 2-camera shoot set up soon. I can go to both boards and I'll edit it later.
You said you could do that with your phone.
Are you gonna have?
I could, yeah.
Are you gonna upload 2 videos, or you combine them?
Combine them. That'd actually be fairly easy to do.
Since they'll both be showing on the same thing, or will show
No,
one
I'd
and
go
then-
back. I'd edit back and forth. That's not hard. Okay, but number 24. Almost the same problem. A couple of differences. This says 1 minus I to the 1/4. Is that correct? Negative 1 minus I to the 1/4. Okay. Where is negative 1 minus I on the complex plane? You don't have to graph these, but I like doing it. I'm seeing lots of pointing. I like Diego's hand gesture. Yeah. Tim, that's a very good way to say quadrant 3. I like that. All right. Or you guys could use your words and say it's in quadrant 3.
Yeah, but that would be no fun.
That would be no fun. So you go to negative 1, and then you go to negative I, and it is where they would meet if we made a rectangle. That's why that's the rectangular coordinate. How far is that from the origin? There's an Easter egg here. How far are you from the origin with that? What kind of triangle have I made?
45.
45, 45, 90. So the pattern from geometry for a 45, 45, 90 triangle where both legs are 1, what's the hypotenuse? Square root of 2. So I am root 2 from the origin.
Sure, I have a question.
Yes?
What's the value of I? I mean, I know it's negative 1, but is that what it is in the I axis?
It's 1 unit from your origin on the complex plane.
But is it equal to 1 over there? So if you have I and 1, is that a square or is that a rectangle because I is smaller than 1?
That's a square. That's a square in the complex
So
plane.
I is...
I mean, complex geometry gets a little different from regular geometry, but remember our first proof of where I came from was you're starting at 1 unit from the origin at 180 degrees, and I has to be 1 unit from the origin and at a 90-degree angle to your original number line.
Yeah.
So it is the same length as 1. It's just in this crazy extra-dimensional 90-degree distance that we proved has to exist. So that's 1 root 2. What angle is this? What standard angle is that in radians?
Radians?
In radians.
It's not as fun as degrees.
220.
So 25 is correct in degrees.
5 pi.
It's
No. 3 pi.
2 pi over
5 pi, yeah, 5 pi over 4. That's correct. Pi over 4 at 45, 3 pi over 4 is your 45-degree reference angle in quadrant 2. 5 pi over 4 is your 45-degree reference angle in quadrant 3. So what we're looking at here is positive square root of 2, positive distance from the origin, cis 5 pi over 4. And that was all to the 1/4 power.
Wait, reference angle?
5 pi over 4 is the standard angle, making a 45-degree reference angle in quadrant 3.
I think you said 5 pi over 4 is your reference angle.
I probably did say it wrong, and I apologize. 5 pi over 4 is definitely a standard angle. Okay, so this is now, okay, what's the fractional exponent way to write square root of 2?
2 over 1/2.
2 raised to the 1/2. And that's being raised to the 1/4 power. This part's a little easier. Cis, well, maybe not. 1/4 times 5 pi over 4. If I raise a power to a power, what do I do with those exponents?
Multiply the base.
Multiply them together, which in this case will just be the denominators, right? So that's 2 to the 1/8. I don't even know what the 8th root of 2 is. It's probably not very big.
32 is
5 pi over 16. That's not a happy angle. It's not one of the ones we normally know. How many roots does this thing have?
Several.
Several.
That's 8. No.
Yeah, you're looking here.
Yeah.
How many roots were we originally finding? 4. So we had a 4th root, so there are 4 roots to this. How far apart are they?
93.
Yeah. If you're in a huge hurry on a test, and you just have to get the answers down and you're running out of time, I would leave my answers, and your book did this on one problem. I know that there's 4 of them, so I know they're 90 degrees apart. Is that one way to say it's 90 degrees away?
Yeah.
What would I add for the next one?
Plus 2 pi.
Plus pi, just to get me that plus 180.
3 pi over 2.
3 pi over 2.
Very good.
And then 2 pi.
No, that would put me back here.
Oh, that's a good point.
Yeah, we only need the print. That's already back at the principal root.
Yeah, you got 4 pi and 4 roots already.
Yeah. So if you're in a hurry and want to get most of the credit from me, do that, and I will get that you understand the concept.
Most of the credit we get?
I wouldn't give you a lot of credit. I wouldn't quite give you full credit. For absolute full credit, and I wouldn't ask you to graph these because that's a pain of a starting point. And I don't want to have any graph paper that has a labeled in 8th roots of 2. But if you have the time, I think it's reasonable. The common denominator here is 16. What over 2 would get me 16? 8 over 2. So this is 2 to the 1/8 cis 13 pi over 16, correct? This would be 16 pi over 16. So that's 2 to the 1/8 cis 21 pi over 16. And that's 2 to the 1/8 cis. This would be 24 pi over 16. So 29 pi over 16. I'm just adding 8 pi over 16 each time. I think if you've got enough time, it's reasonable for me to ask you to remember how to add fractions of common denominators. That's not a pretty one. And it's a little bit unfair to ask you to graph like 5 pi over 16 without a calculator. It's doable, but it's whatever 225 divided by 4 is, which is what, 56 and 0.25, somewhere around there. So that'd be a pain. Any questions on how I did it? And how I figured out where the roots were? Nope.
Where are you getting the plus pi over 2 plus pi plus 3 pi?
It's got 4 roots, evenly spaced. Now, only because it's got 4 roots, evenly spaced around a circle means every 90 degrees, 360 divided by 4. If we were looking at cube roots, they'd be spaced 120 degrees apart. If we were looking at 5th roots, they'd be spaced 72 degrees apart. So I know I'm looking for 4 of these things 90 degrees apart. Well, what's 90 degrees past 5 pi over 6? 5 pi over 16, excuse me. That's 5 pi over 16 plus 90 degrees. That's what pi over 2 is. Then if I want to add another 90 degrees to this, well, that's like adding 180 to my original. 5 pi over 16 plus 180. And then I'm going to add 270. This is just me adding 90 more, and adding 90 more to find the other 3 points. Since that starts around 56 degrees, this does look, these answers do on the complex plane look something like 45, a little higher. Here, here, here. Something like that. The points would be these 4 points, just a little bit past, starting a little past 45 degrees, and then I add 90 each time. It's another way to add 90, add pi over 2 each time. Any questions on that?
No.
Okay. I want to show you guys one new use for this. This is not a new idea. It's actually an old idea, but you can do more with it. It is... Okay, they look like... Okay, let's go back to Algebra 2 for a moment.
Is this something we should be writing down?
Yes, these are new notes. There's a couple of new examples of what you can do. And these are complex solutions. This almost sounds like a chemistry class for a second. On today, January 16th, 2013. Complex solutions. You've done the idea of this before. Quick example from Algebra 2. If x squared minus 1 equals 0, what's an Algebra 2 solution for that?
Square root of 1.
X squared equals 1. So x equals plus or minus
1.
the square root of 1, or just plus or minus 1, correct?
Yeah.
Interestingly enough, de Moivre's theorem still works here. From this step, you're actually asking yourself, what are all the roots of 1 cis 0 degrees? And there's 2 roots spaced 180 degrees apart. In Algebra 2, in Algebra 1, you should have been able to do this. In Algebra 2, you should have been able to do this. Correct? Because it's something you would then say x squared equals negative 1. So now, x equals plus or minus the square root of negative 1, which you later learned was this weird number called I, which you didn't really learn where it came from or what it was used for, but we started to touch on that last week. Any questions on either of these two examples?
Erase.
Want to erase them?
Me.
We're good. Do my next example up here. Now you're ready for this. X to the fifth plus 1 equals 0. In Algebra 1, you were expected to solve something like this. In Algebra 2, you're expected to solve something like this, and the idea of complex numbers was introduced. Now in Precalculus, you follow the same steps, but you add de Moivre's theorem. At least that's how I'm going to ask you to do these. Yes, sir. Hopefully it's picking up the sound. Hopefully I'm talking loud enough. Good point. I did forget the boom mic today. Someone might have to listen to this one louder. So my steps here, I again subtract 1 from both sides. And now x is going to be all of the fifth roots of negative 1. All of the fifth roots of negative 1 will be possibilities. How many fifth roots? How am I going to do this now? Do I want to do this in rectangular complex coordinates?
Oh, I'm actually.
No.
Okay. Turn negative 1 into polar complex coordinates.
Maybe 1 cis pi.
1 cis pi. Very good. 1 cis pi. But that is all being raised to the 1/5 power, because we're looking for the fifth root. So my principal root is going to be 1 to the 1/5 power, cis 1/5 times pi, which is 1 cis pi over 5. How many degrees is pi over 5? He just pulling out his calculator to do 180 divided by 5.
36.
36 degrees. Yes, that's 36 degrees is where that's going to start. I'll let you do these other roots, and we'll move back over to this column. I will let you do these roots in not in radians, because this is a bit of a pain. 36 degrees. How many roots do I have?
5.
How far apart are they on my circle?
72 degrees.
72 degrees. Diego keeps his calculator and a unit circle handy. That's how he knows all these answers so quickly. So my next answer is going to be 1 cis 36 plus 72, that's 108 degrees. My next one is going to be 1 cis 180. Is that correct? And my next one is going to be 1 cis 252. And my last one, before I would start repeating myself, what is it?
You're adding, oh wait, no, you're adding 72. Well, never mind.
Yeah, so it should be 324,
324.
which then would get me, another 72 would take me right back to here, so we'll stop there. What's this 1 cis 180? What's a simpler, old school, older way of writing that?
1 cis pi.
1 cis pi, that's radian way. Does this have a non-real component?
No.
No, if it's 0 or 180, it's on the x-axis. That's just -1. Which would have been your only answer in Algebra 1 or Algebra 2. You would have just said, oh, that's -1.
But now we get to add all this fun stuff.
Yes, and you would have been 20% correct.
That's worth something, kind of.
I love the Moivers theorem, I really do. So from here, I do love it.
Complicated. It's pretty simple.
Now from here, the equations do get a little bit uglier. And you might have to remember some factoring or some other things going on. Let's see if I can do a quick example of one. Not liking that one as much. All right, I'll hold off on that one. Okay, may I erase the board?
Yeah.
Okay. Okay, so, quick example. 3x to the 4th plus 48 equals 0. What are my first steps here?
I've got the x, or leave the x. That's all.
Okay, that's my goal. Alright, I'm going to say my first step is to subtract 48 from both sides.
You can do that.
Alright, I was going to look for something a little bit more specific here. Okay? I'm going to go ahead and say my next step is to divide by 3. And -48 divided by 3 is -16. Now, if this were x to the 4th times positive 16, x to the 4th equals positive 16, would you guys know the answer? What is that? I'm getting Robbie holding the right number of fingers, and it would be 2. So we'll see if that's a factor in our answers at all. So now we're looking for x to be all of the possible 4th roots of -16. Okay? I don't like doing this in rectangular form, so I'm going to change -16 to positive 16 cis pi, which means, oops, and that is to the 1/4 power. So I'm actually looking for the 4th root of 16 cis pi over 4 as my principal root. What's the 4th root of positive 16?
2.
So I got 2 cis pi over 4. How many roots do I have? Robbie's holding up 4 fingers. How far apart are they? 90 degrees. That's 360 divided by 4. I was waiting to see what gesture Robbie would do for that.
I know.
And as we just saw when they're 90 degrees apart in radians, adding 90 is pi over 2 or 2 pi over 4. So that's where the faster way to get 5 pi over 4 or 7 pi over 4 or I skipped 3 pi over 4.
You did.
I did. I added 180 from here. Sorry that those are out of order. So those are my 4 solutions to this equation. None of them are on the x-axis, so this has no real solutions. This were a parabola, it would not intercept the x-axis. But it does have 4 non-real solutions. Any questions on that? Okay, so your homework tonight is not that much, it's just,
Is there more of this?
it's just solving equations, like this. And it's, and I did some of them on the board actually, more than I meant to. It's 26 through 3rd page. It's 26 through 31 all, and I did 2 of them with you. It's still page 605. And the review work, which is on the study guide for tomorrow, is page 608, 11 through 61 all, I think. So if you want to start this as well, you may.
What does that do?
That's review work for a test, so it's never due, but if you hand it in to me as you walk into the test, I will check it off for 1 or 2 missing homework assignments or a little homework extra credit. So any of you missed some homework, if you get all of that done showing work, the more you show, that's a lot of work.
Yeah,
The more
can
you
we
show,
still
the
get
more-
credit if we don't do all of it?
Yeah, get something if you don't do all of it, but if you're missing a couple homework problems and you do it all, homework assignments you do it all, that would be very, very good. I'm not going to say specifically how much until I see how your work looks. Yeah, go ahead and turn off your